Okay, so what we are doing today is the fundamental theorem of calculus. It's pretty important, thus fundamental. And it's one of the few things you actually get to abbreviate in calculus, FTC. This deals with it a little bit in this piece right here, the g of x equal to the integral from 0 to x of f of t dt. Now, this is the type of thing we're going to be working with where we don't have a graph and we have a function to evaluate it. But for you, you actually have the graph, so you didn't need the fundamental theorem of calculus to accomplish that integral. But then the b, c, d, that's just kind of going back to what we know about first, and second, third things. So, first let me orient because it's already off. Now, with any type of free response problem where they give you a graph, make sure you know what it is you're working with. Here it said the graph of the function f. Hey, it's our original graph. That's good to know. So many times they throw the derivative at us. Okay. Consists of... Yeah. What? Okay. So f consists of a semicircle and two line segments as shown above. Let g be the function g of x equal that. Okay. So, as Amelia was saying, there's actually that connection between that and the derivative. We'll get there in just a moment. Okay, so A says find g of 3. So g of 3 equals from 0 to 3 of f of t dt. Do we agree with this? Or just simply, instead of g of x, it's g of 3, so we're taking 3 and putting it in for x. Alright, what does an integral from 0 to 3 mean that we need to do? Find the area underneath the curve specifically from 0 to 3. So I want this piece and this piece. Okay. Now, again, they want to see where your numbers are coming from. So although you can do some work outside, make sure you translate it down here. So we have our area is pi r squared divided by what? 4. Good. Okay, and what's my radius here? 2, so would we agree that it's just pi? Okay. And this can be a positive pi? Yes.
It doesn't like say in terms of pi, so could we do either?
Ooh, yes. Great question. You want to go ahead and leave it in terms of pi because it's. I would think this to be a non-calculator one. Would be my assumption. Good question. Alright, so this is positive area. Now when we go from 2 to 3, we've got an itty bitty triangle here. So area equals 1/2 base, which is 1, times height, which is 1. So it's just 1/2, but it's below, so it's going to be a negative 1/2. Do we agree with that? Okay. So I'm going to go ahead, I want to show actually both pieces here. So it's going to be pi plus negative or pi minus 1/2, either way is fine. And that's going to be my area. We don't have any units, so we're done with that. Raise your hand if you got that right. Awesome. Okay. Now B says find all the values of x on the open interval at which g has a relative maximum. Okay. So my justification for a maximum is that, let's go back to, so f of x as a maximum when my derivative goes from what to what? Positive to negative, right? That's what gives me my top there. Positive slope to negative slope. Okay, so that's what we're looking for. Now we want to know where g has a relative maximum. So what we're looking for is when g prime of x goes from positive to negative. Well, I don't have g prime of x. I only have g of x. Now this is where today's topic is going to come into play with what we're doing here. What do we know about derivatives and integrals in terms of operations? Yeah, one goes one way, the other goes the other way. They're inverse operations. They undo each other. So essentially what we have then is that when we take the derivative here, we're going to, in a way, get rid of that integral. Okay, so let's actually okay. Let's come back to this. So hold this nearby, because I want to actually go and formally define what we do with this here. But what we're going to have happen is that when we take the derivative, it ends up being just f of x. Because taking the derivative of both pieces cancels out the integral. Okay? So this is to be considered. So with that being said, go ahead and get out a piece of paper, or you can continue on here. Our notes for today are going to be handwritten. Turn it back a little bit old school. So if you want to continue it from here, or get out your piece of paper, you're welcome either. No, oh no, it's just clean. Don't look. Okay. So today we're talking about the fundamental theorem of calculus. Now, your homework for tonight, I think, says 3-4. So we'll just call this 3-4. Not mine. All right, fundamental theorem of calculus. I'm going to use THM to represent theorem. Calculus. Parts 1 and 2. Does theorem take you back to geometry? Isn't theorem a weird word? It's THEORM.
Yeah.
There's lots of weird ones, like smudge. Say it enough times. You gotta say it like, so they're like smudge.
Yeah.
It's like fudge.
Theorem is a statement that has been proven true. Theory is only true. Theory of science, Does that sound good? Okay. A little bit of history, math history for you. Make sure that. Story time. Okay, so the fundamental theorem of calculus is appropriately named because it establishes a connection between the two branches of calculus, differential calculus and integral calculus. Differential calculus arose from the tangent problem, so like the slope of the tangent, so doing the derivative. Whereas integral calculus arose from a seemingly unrelated problem, the area problem, so the area of the curve. So there were two separate things of that people didn't know was related for a long time. Until Newton's mentor at Cambridge, Isaac Barrow, he lived from 1630 to 1677. Oh, forgot I lived there 7 years. Discovered that these two problems are actually closely related. In fact, he realized that differentiation and integration are inverse processes. That's what we were saying. They kind of undo each other. And the fundamental theorem of calculus gives the precise inverse relationship between the derivative and the integral. So it's what bridged those two chunks of calculus. It was then Newton and Leibniz who exploited this relationship and used it to develop calculus into a systematic mathematical method. In particular, they saw that the fundamental theorem enabled them to compute areas and integrals very easily without having to compute them as limits of sums, something that we do not do yet because it's kind of crazy. So, when we first did integrals, we looked at Riemann sums, which we said if we were to take infinite, as tangible as infinite is, rectangles and add those areas together, that's what gave us the area underneath the curve. So back when they were first learning about area underneath the curve, they would do the sum, the limit of that sum as n approached infinity. That's how they found the area underneath the curve. And separately, they were also doing that differential calculus where they were taking the derivative and learning about that. And then Mr. Barrow came along and found the connecting piece between the two, that derivatives and integrals actually relate to one another and that they're inverse operations, they undo each other. So the fundamental theorem of calculus allows us to actually evaluate definite integrals without using geometry, area underneath the curve, and a calculator, specifically for us. Okay, now, interestingly, depending on which textbook you look at, which resource you look at, some will call part 1, some will call it part 2, so it doesn't really matter that one's part 1 and one's part 2. When you refer to it, you can just say fundamental theorem of calculus. Alright, so let's start off with what I have classified as part 2. I know it's weird we're starting off with part 2. So part 2 of FTC, fundamental theorem of calculus. If f is continuous on the closed interval a to b, then the integral from a to b of f of x dx. I didn't say the punchline. Equals. Okay, so it's not going to be capital F of B minus capital F of A. Let's catch up to there so that we can see what capital F means. So if F is continuous on that closed interval, then the integral from A to B is capital F of B minus F of A, where capital F is any antiderivative of F. Who remembers what that means to be an antiderivative? Yeah, it's the function that when you take the derivative, it gives you that. So in other words, if I take the derivative of capital F, I will get lowercase f. So it's the function that when we take the derivative gives us our starting point. It's what function, capital F of x, if I take the derivative, gives me lowercase f of x. Okay, so that's what we were doing last class with our integration rules. Right, Drew? Perfect. All right. So, but that was with indefinite integrals. We're looking at definite ones. Okay. So all this is saying is that we find that function. So before we would, do the reverse power rule. If you would, we'd add 1 to the power, divide by our new power, have our plus c, and that plus c represented the family of functions where it was the same function but shifted up and down all over the place. Right? We had infinite possible solutions. Now, when we have the definite integral, we're saying, all right, we can take any of those antiderivatives and use it specifically from b to a, or at b minus that same derivative at a, or that same antiderivative. Now, we can use any antiderivative, which means we can use the one where the constant is just 0, and thus we don't have as many numbers to work with. So that's typically what we do. So this sounds more complicated than it actually is. Let's take a look at an actual problem with it. So our first example, let's go ahead and evaluate from 1 to 2 of x squared minus 3 dx. So before we would graph this, use geometry to find the area underneath, or use your calculator. Last class, or 2 classes ago, we evaluated this where it didn't have those bounds. And we would just go and say, blah, 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 plus. Well, now we have bounds, we actually evaluate. So what we do is we first integrate, or find the antiderivative. So just like before, what's the integral of x squared? Good, x cubed over 3. So same thing, the antiderivative is add 1 divided by my new exponent. Minus, what's the antiderivative of 3? 3x. Good, 3x. Now we don't need the plus c because the plus c was just telling us the general solution of wherever our curve was. We're actually evaluating this from 1 to 2. So here's a little bit of different ways of notation. Some people, some books will use bracket to indicate that we are integrating here, evaluating that integral from 1 to 2. Sometimes you'll see it where it's just a vertical line from 1 to 2. I think I've even seen large parentheses. That one's not as common. I'd say these are the most common. So this just simply says, hey, I've got my antiderivative, now I need to evaluate it at these 2 points. Okay, so are we good so far? We've just done the antiderivative, and we're specifying where we're going to evaluate it. Okay. So now, according to this, we do the antiderivative at B, the upper bound, minus the antiderivative at A, the lower bound. Okay, so I'm just going to literally take 2, put it in, so 2 cubed over 3 minus 3 times 2. I'm going to go and put a big parentheses around there because it's f of b minus f of a. And I want to subtract that whole next piece. So I first took my b value and put it in. And then I'm going to subtract from that my a value. Substitute it. Okay, so I have then 1 cubed over 3 minus 3 times 2. I know we don't have to simplify if it's free response, but let's go and simplify just so we can kind of get an understanding of what's happening here.
Maybe you can leave it like that.
Free response, you can leave it like that. No complex fractions. You're good to go. Please don't simplify it. Alright, so we get 8/3 minus 6. I'm going to go and distribute this because it makes me nervous. See, I already messed with it. Minus 1/3 plus 3. That's my final answer for there. Some weird number. What's 8/3 minus 1/3? 7/3. Negative 6 plus 3? Negative 3. Now, we're going to want to combine that. So let's go and say negative 20s, negative 9/3. Does that make sense right there? I combined and gone ahead when I got from down here. So what would that actually equal? Negative 2. Give me age width and plus 1. So my area under that curve from 1 to 2 is negative 2/3. Now, what does that mean? It's negative 2/3. What does that negative mean? Yeah, and it might not be that all of it is underneath, but that the majority of it is underneath. And if we think about what this is, though, if I think about my graph, pretend that went through, wouldn't that be underneath the curve? So that makes sense for it. So what we just did is we went ahead and evaluated this the way that our calculator would have. Found that area underneath the curve from 1 to 3. So something like that. Okay. Questions on what we did there? Okay. Now I want to make sure we understand the distinction between the indefinite integral and the definite. This is my definite integral. And as we can see, my definite integral gave me an actual number, the actual area underneath the curve. Whereas my indefinite integral, if I were to just integrate this, x squared minus 3 dx, this would simply be x cubed divided by 3 minus 3x plus c. And this is just, it returns a function. This is the function, the antiderivative, that when I take the derivative of it will give me this at any point, at any c value there. So definite integral gives me an actual answer. Indefinite is that plus c.
Why are you finding the area from 1 to 3 and 1 to 2?
Because I meant 1 to 2.
Oh,
Thank you. That does say 1 to 2, doesn't it? So pretend. Yes. Thank you. So again, definite gives me an actual number, indefinite gives me that function. It's kind of like if we think back to our derivatives. If I took the derivative, let's just say of x squared plus 1. My derivative here would just be 2x, right? It gives me back a function. But if I did the derivative of x squared plus 4, evaluated at x equal to 0, that's the easiest. That is when I find my actual derivative and take 0 and put it in. So we would end up getting 0. So notice my general derivative gave back that function. The specific derivative at a point giving back 0. And this is where the notation is kind of similar. In that bracket, we're evaluating it from 1 to 2. Here we would say where we would evaluate it x equal whatever. But that's kind of the catch. Questions on that? So let's go and take a look at another one just to kind of solidify it. We won't do trig just yet. Let's go from 1 to 4 of 3 root x dx. Okay, so if we want to go ahead and find our antiderivative, I'm going to rewrite this with my fraction exponent. Okay. Now remember, my 3 can just come out in front. We can leave it in there, we can bring it out in front. It's up to you. The numbers don't look too bad. I'm going to go and leave it in, but you're more than welcome to take it out. So my antiderivative would be 3x to the what? 3 halves, right? And we would have to divide by my fraction. I'm going to go ahead and multiply by the reciprocal. Because I know dividing by the fraction is going to cause me to multiply by the reciprocal. Times 2/3. And again, evaluated from 1 to 4. Sometimes you'll see two people don't use that left bracket. I think it's to get in the habit of doing that, because sometimes on free response questions, it won't be just an integral, will be like 10 plus the integral of that. And you want to make sure you distinguish that 10 will not be part of your answer. Alright, this actually simplifies for us, right? That's nice. So let's go ahead and evaluate. So again, f of b minus f of a. So 2 times 4 to the 3 halves minus 2 times 1 to the 3. I recommend you take the root before you raise it to the power. The square root of 4 is 2, cubed is 8, 16 minus 2. Do we agree with 14? It's okay to say no, I made mistakes.
Yep. I agree.
You agree? Are you
Yeah,
sure? Did you check it? Okay. So my area underneath the curve is 14, quite a bit more than that last one, right? Which, if we think about it, square root curve doesn't necessarily have a large gap, but when we multiply it by 3, that stretches it and creates a much larger gap for us to have area. Okay, questions with that? Alright, let's do one more like this, and then we'll take a look at the other fundamental theorem calculus. Yes, the more exciting. This is going to be a little bit wordier. Find the area of the region bounded by the x-axis to find the area of the region bounded by the x-axis. The function y equals 3 minus x times the square root of x equals 0, and x equals 3. So find the area of the region bounded by the x-axis. The function y equals 3 minus x times the square root of x equals 0, and x equals 3. It's bounded by these 4 things. It's bounded by the x-axis, the curve, and those 2 lines as well. So we have the area that's bounded by all 4 items. So to help us kind of visualize what in the world this is even asking for, let's do some kind of sketch. Alright. Do you guys know what this looks like? No, me neither. Let's make some. Alright, does it at least go through 0, 0? Yeah, right? Okay, so we at least have 1 through 0. So, I don't know what it looks like, you don't know what it looks like, but we want some type of graph. Okay. Now, it says bounded by the x-axis, this function, and then x equal to 0 and x equal to 3. What are x equals 0 and x equal to 3 on a graph? What kind of straight lines? Because all lines are straight, right? Horizontal?
Vertical.
Vertical, vertical. So we have, let's just go and throw in 1, 2, 3. Would you agree this vertical line? And this vertical line? Okay. I'm making it up. I don't know what it looks like. I made it up. Okay, so it just says the area of the region bounded by my x-axis, the curve, and these x values. So all I'm doing is finding this area here. Does that make sense there? The x equal to 0 and x equal to 3 is really just what on my integral? Yeah, it's just the bounds. It's just telling me my interval. So it's just another fancy way to say, find the area of the region bounded by the x-axis. It's another way of just saying go from 0 to 3 of my function in dx. That's all that this is saying. The fact that it's bounded by the x-axis is what lets us know dx. But it's just another fancy way of saying find that integral from 0. Okay? So don't be thrown off by AP messaging. Okay, do we have a product rule for integral stuff? No, so what do we need to do first? Multiply it out. So I'm going to go ahead and rewrite this to the 1/2. I personally struggle with thinking square root. It's 1/2 if I don't write it down. So now I'm going to go and multiply, so I have 3x to the 1/2 minus, what's x times x to the 1/2? X to the 3/2. Now make sure you still carry along all of your proper notation. If you just wrote that and didn't say anything more, you would lose points because your notation is horrendous right there. So we've got a couple of things causing issues. We lost our bounds, and we lost our dx. So make sure you carry those along the whole time until you actually evaluate them. Alright, we have questions so far? Okay, I want you guys to go ahead and try evaluating this. Again, find your antiderivative, then evaluate it at your upper minus your lower. think you have your answer, check with someone nearby you. I'm going to put the work up here for you. Okay, I got a little carried away with my simplifying. Did we at least get to this point here? Is there anyone that needs me to go over how we got there? Darrell, you're good? Okay. So my antiderivative, we want to go ahead and add 1 to my power. So I got my 3/2. Divide by my new power, but divide by 3/2, just multiply by my reciprocal. Same thing here, add 1 to my power, so 5/2. Divide by that or multiply by my reciprocal. So this piece is just simply my antiderivative. Okay. Are we all good with the antiderivative?
Yeah.
Yes,
How do you know you're going from 0 to 3?
Because they gave me the bounds here. And we know that because it said bounded by x equals 0. Good so far? Okay. So then I just went and simplified my 3's here. So I had 2x to the 3/2 and 2/5 x to the 5/2. So now I just simply take 3, put it in to each piece. So that's this here. So this is f of b minus, and I took a and put it in. Now when I take 0 and put it in, I'm going to 0. So this here is f. Okay. And then I went ahead and simplified. Did everyone simplify that much?
Yeah.
Good, same thing?
I got 12.
And then you could keep going. But again, for response, we can literally stop right here. There's no complex fractions. Okay. Questions on that one? Okay, here you go. You're looking at me, buddy.
Yeah.
Okay. All right. So now let's take a look at the fundamental theorem of calculus, part 1, technically. And again, it really depends on. Yes, sir. Yeah, of course you're allowed to ask a question about this. So what I did. So if I look back at the 3/2, I can't take the square root of 3, so it's the square root of 3 cubed, which 3 squared, square that brings me to 3 root 3. Does that make sense? But does that one make sense? Okay, so then the square root of 3 I still can't do, so it's the same thing as square root of 3 to the 5th, which I essentially broke up into 3 to the 4th times 3. Square root of 3 to the 4th is 3 squared, which is 9. 3. So I was just trying to impress you guys with my mental math. Did it work? Okay. But the next talk here, I was like, no, fractions. Okay. Other questions on this piece? Okay. So now what I feel is the more exciting thing. Now what we just learned is huge. It is vital to evaluate any definite integral by me. But now the more exciting part, kind of the more mathy part. So technically part 1 in most textbooks. Okay, I want to make sure I give you the good wording. Actually, let's do a problem first. I'll leave a space there. Okay, so we're going to kind of see what this is by first doing this problem that used part 2. So find the derivative of the function. You guys are going to love this function. Don't worry, there's no period. Of the function f of x equal to the integral from -2 to x of of t squared, I'm running out of room, minus 2t plus 5 dt. Okay, I need to rewrite that, I'm sorry. So negative 2 to x of t squared minus 2t plus 5 dt. So our function is an integral. Okay. And it's still a function. It's based upon x. X is one of my bounds, though, which is interesting. It's okay. So they want us to find the derivative of this. So let's go ahead and use FTC for it too that we were just doing. We can do this. Okay, so first, let's go ahead and find what f of x actually is, right? Before we take the derivative, let's go and find out what it actually is. So we need our antiderivative. Basically all we're doing is just evaluating this definite integral. Okay, so I'm just doing what I was doing before. So my antiderivative would be t cubed over 3 minus 2t squared over 2 plus 5t. Do we agree that for our antiderivative? Okay. And this is getting evaluated from negative 2 to x. Yes?
I don't understand why.
I'm simply wanting to evaluate this integral. So I need to evaluate the integral so then I can actually have the function and take the derivative of it. So right now we're just going ahead and doing this as if it was a problem we had 2 seconds ago. Okay? Alright, so again, take your top bound, plug it in, minus your bottom bound, substitute it. Yeah, we're going to have a variable in the end, but that's okay, right? It is a function based on the variable x. So let's go ahead and do this together here. So I'm going to start off, let's use different colors. Take x and substitute it in. So I have then x cubed divided by 3. I'm going to reduce that. Minus x squared plus 5x. Okay, so this is just f of b, right? I'm just taking that first down and putting it in. Minus, take negative 2 and put it in. Negative 2 cubed over 3 minus negative 2 squared plus 5 times negative 2. This is just okay, so I'm just in my definite integral like I did before. So do we agree with what I've done so far here? Anyone have questions? Pieces that we're not understanding? Okay. Now, yes, we can simplify. Would you agree this simplifies down to some constant of some sort, right? Okay. But I'm going to let you know we don't need to save ourselves time. So this is my function f of x, right? Whatever that simplifies down to, that's my function. But they didn't want the function. They want us to find the derivative. So let's go ahead and find the derivative. F prime of x. Okay, so what's the derivative of x cubed over 3? X squared, right? So I bring down my 3, that reduced. I'm going to write out each piece just so that we don't lose it. So I brought down my 3, and then my 3 is reduced. What's the derivative of x squared? What's the derivative of 5x? What's the derivative of all of this? 0, right? So my derivative was just x squared minus 2x plus 5. Now, we can do that every single time they ask a problem like this. What if my lower bound instead of being -2 would have been 158? How would that change my answer? I changed this -2 to be 158. Take a look at this. How would that change my answer? Turn and talk to your shoulder partner. How would it change it? They're inverse. So just higher and stronger. That's
why I don't want to. I want to be really kind of like.
well, the area it's more so an indefinite one that will get back to
So I think we just take oh, this whole value. Oh, so we don't have to do all this.
because it's not that the slope in here. Alright, what should be fine? If I change my lower bound, if I change this guy to be, what did I say, 158, how would that change my derivative here? It doesn't! Why? Because this is just simply a constant at the end, right? And when I take the derivative, any derivative, or the derivative of any constant is just 0. So, now, what connection do you see between this?
Wow.
All I did was a highlighter here. I haven't even underlined yet. And this!
Oh.
There you go. Good tag. What do we notice?
It's the same thing.
It's the same thing. It's just my x replaced all the t's, right? Now, as we saw, this will happen regardless of what that lower bound is. So this brings us to FTC, part 1. Alright, let me make sure I have my proper terminology here. If f is continuous on the closed interval a to b, that might seem like a minute detail. It is pretty important, although I will say I haven't seen the AP exam ever try to trip you up with that, but you never know. So it needs to be continuous on the interval over which we're trying to take the area. If f is continuous on this interval, then g, which is defined by g of x, is equal to some constant a to x of f of t dt. So similar to what we had down here. We have a function defined as an integral with that variable as my upper bound. Okay, so if f is continuous on the interval, then g is continuous on the interval. Whoops, that should be close. And it's differentiable. G of x. And differentiable on the open interval a to b. I'm going to throw something else on the end, but I want to let you guys catch up. So if f is continuous on that closed interval, then g, being in this funky format, is also continuous on the interval, but it's also differentiable on that interval. And when we actually take our derivative, as we just saw, it is simply f of x, or whatever our function is with that variable substituted. So this is the idea of where that derivative and inverse undo each other. When I take the derivative, I essentially lose that integral and replace that variable. Okay, so I'm going to highlight a couple of key things here. Oops, I wanted yellow. That's okay. Alright, now there's a couple of important pieces with this. X must be the upper bound. Okay? Now, as we saw, a could be any value. I don't care if it's 0, negative, or positive, or pi. Pi is just a constant. But my variable needs to be in the upper bound. If my variable is not in the upper bound, we need to use our properties to flip-flop that. So, just a reminder. If I have from a to b of f of x dx, I can switch those bounds and negate it to get the same. Okay, so if for some reason x is not your upper bound, just apply this property, switch it and negate it, and then you can use the FTC. Now also, notice that this is just x. It could be a different variable, it could be like g of u from a to u, or g of l, sure, from a to l. But when we have something other than a function up there, then we have to change things. So we'll talk about this. Okay, so those are kind of the technicalities. Questions before I have you do another practice problem? I think it's pretty cool. It's like a shortcut. You don't have to do this every single time. You can go just boom to your answer. So, with that being said, let's have one of those boom moments. Alright, g of x equals the integral from 0 to x. Ooh, let's go crazy. You guys ready? I have to be careful I don't go too crazy though. Okay, then I won't go crazy.
Whoa. Still too crazy.
Yes, Libby? What, right now in this crucial moment? After this problem, you can go, but you better hurry back because there's more to go. Oh, sorry, I didn't tell you what to do. Thank you. Alright, find g prime of x. That's kind of an important piece. Alright. So g of x is this crazy integral dealing with cosecants and exponentials that we haven't even learned how to integrate nor take the derivative of. And I want you to find the derivative of this. Alright. What do I do?
Place the g's with their x.
Now, make sure you say g prime of x equals, because if you just say equals, you're saying that g of x equals something completely different.
I did that one.
Yeah, go through it again.
Yeah.
Alright, so g prime of x equals what?
Cosecant.
Cosecant squared
Parentheses x squared. Parentheses x squared.
of x squared. Yeah.
Yeah.
So I'm just taking x, literally putting it in. Okay.
Plus e of x.
Plus e to the x. Anything else?
Wait, what else? Oh!
Right? Because that FTC part 1 just simply says, like we saw, doesn't matter what my lower bound is, because that constant's just going to go away. And essentially what it is that derivative and integral cancel each other. So really, it looks crazy, but all you do is replace that variable.
Why is there different variables?
That's a great question. Really ask, why is there a different variable to begin with? So you're not going to get a very eloquent answer here, but we call this the dummy variable, which essentially is saying that, so we could have used something other than this, right? We could have used t, we could have used v, this could have been in terms of dx. But this is just representing some x value along the way. And so we cannot have it be the same thing, because then we have issues with technicalities of doing it with respect to what it is. So it just needs to be different. They'll give it to you always as a different variable.
How is it not the same as in you can define we're going from this point to this point on the x-axis and it's relative to the x-axis? Why can't you say that?
I told you weren't going to get an eloquent answer. So I'm going to pause you there and direct you to the textbook from there. My explanation is that we need a dummy variable because they can't be the same. Then we'll talk after. Okay. That's a good question. Are we good with this? Does that make sense? Okay. But you know, we can't always leave it that easy, right? So, what about... I don't want to do too crazy. Hold on. Let me make sure I get the right problem. I want it slightly different. Ha. Nope. Wrong one. We'll just do that one. Okay. G of x equals 7 to x to the 5th. And we'll go relatively simple here. Square root of sine of t dt. Prime g prime of x. Okay, so this kind of changes it up a little bit. What do we notice is different about this problem in comparison to the previous problems I've given you? Yeah, we've got something more than just x here. This is x to the 5th. So this slightly changes things for us. What this means is that we have to consider chain rule. Okay, so bear with me. Let's go ahead and write out kind of a variation of our fundamental theorem of calculus, part 1. Okay. So we'll just write in a side note here. If g of x is from a to u of x. So basically what this is saying is this is some function of x of f of t dt.
What does that have the lower bound?
A. So this is still just some constant. The upper bound is u of x. And that was supposed to be here. Okay, so all this is saying is that we have something more than just x up here. Okay, so it could be sine of x. It could be natural log of x. For us, it's x. Then g prime of x, and this may look funky, but write it down, bear with me, we'll take a look at what it is f of x, sorry, f of u. We're still taking this and putting it in like normal, right? Hold on with me. Times u prime of x. The being was
V of x equals what's that? Is that 4x?
This is u of x.
Oh, that was k.
K? How'd you get K out of that?
So if we're taking the function of a function, we're putting a function inside the variables of another function.
I know. So this is where it gets kind of crazy, okay? So what this is that we have to take in consideration chain. Because we're essentially doing it up here, but what's the derivative of x? 1, which doesn't impact our answer. So what we have happening here is that when I'm taking my derivative, I now have a function inside a function. So let's just real briefly, you don't have to write this down, but I'm going to remind you. If I had f of g of x, or I had an inside function, when I take my derivative, f prime of g of x, we would have to then multiply by the derivative of the inside, right? So when I took my derivative of all this, I would take the derivative of the outside, inside stays the same, times derivative of the inside, right? Okay, so essentially we're doing the same thing. This is essentially coming from my chain rule, that I have to multiply by the derivative of the inside. My inside is that function that I just shoved in there. Now, you may be asking to yourself, and afraid to say it out loud, but Mrs. Margraf, there's not a prime here, but we have a prime here. But remember, we're doing the derivative of an integral, so it essentially cancels out. So, it looks crazy, but it's not that. Let me get rid of this here. Let me just get more space. Okay. Okay, so we're going to do it just like we were doing before. G prime of x. So I still take this and I put it in for t. Okay, so it's still going to be square root of sine of x. But now I have to just simply multiply by the derivative of this function. And what's the derivative of x to the fifth? That's all that changes. We're still taking that, putting it in, but I multiply by the derivative of the inside. Oh, 5x to the fourth, thank you. The sine still. We're doing the derivative of the inside where this is my inside. So I'm taking a function and shoving it into my current function. I have to do the chain rule derivative of that. So again, it's what we were doing before. It's just I didn't make you write times derivative of x, which is just 1. So again, we took x, put it in, wherever we saw t, and then essentially we multiply by the derivative of x, which is just 1. So it didn't really make a difference for us. So when I have something other than x, I have to, after I've shoved it in, multiply by the derivative. Okay?
So who think that you give up the side derivative 5 sine x to the power of 4?
I'm doing the derivative of whatever it is I shoved in. Yeah. Not the derivative of sine x to the fifth. Derivative of whatever it is that I shoved in. Okay. So again, the reasoning for that is because of the chain rule. Because we're taking the, when I'm going g of x to g prime of x, I'm technically doing the derivative, which means I have something inside my function here that I need to multiply by. So this is all that it changes when we have something other than just x. You have to multiply by the derivative of that. That's the thing that most people forget. So be very cautious. All right, questions on that? Yes.
You know, sometimes you have to plug the x in more than once.
Mm-hmm.
Do you multiply by the derivative of it, for each time that you plug it in?
Just at the end, it would be so if I did up here, it'd be one big thing times that derivative. That's a good question. Other questions? Okay. So let's go ahead and do one with that. Yes.
Why are we taking the derivative of the entire square root sine x of sine x to the fifth? Why aren't we taking the derivative of that entire thing.
Let's see if I can explain this one. Yeah, I think we can. Okay, so what we have happening here is g of x is equal to the integral from -7 to x fifth of, this is some function here, I'm just going to call it that. F of t is square root of 7. So when I go to do my derivative, what I have then is the derivative of this guy. Which when I do my derivative of this, so essentially when we go back to doing this thing, I have, if I were to first evaluate this here, I would have f of x minus, well, my anti-derivative. I'm going to call it that. Minus f equal of -7, but then I have to do the derivative of that. Does that make sense? Okay. So when I do my derivative of this, that cancels that out, right? So it gets me back to my original. But this is not in terms of t. So I have to do that. I have to do the derivative of this. It's different than what I had before, so that's where my chain rule comes in. And then the derivative of this is just, it's a constant, right? So here that's 0. So it's my function with that plugged in times the derivative of what I plugged in. This became my inside of my function. Yes. And the textbook also is that. You challenge me, and I appreciate it. Alright, other questions on this? Okay, so let's do another one just to kind of solidify this in our brains because it is weird. But again, all that changes is we have to do derivative of whatever we shoved in. Alright, so let's go ahead and say f of x equals the integral from pi over 2 to x cubed of cosine of t dt. F of x equals the integral from pi over 2 to x cubed of cosine of t dt. Wait, what's the cosine of pi over 2?
0.
0. Is it 1?
0.
Is it 1 or is it 0?
0.
0, good. Who said 16? Remember, make sure you know your trig line is over. Okay, so again, my derivative. So we see it is a constant to some function. So I'm just going to take this, put it in. So instead of cosine of t, I have cosine of 1. X cubed. And derivative of what I just shoved in is 3x squared. And that's it. Try to make sure that your prime is more distinct from your f than mine was. So again, you just take that, substitute in like before. The only difference is now we multiply by the derivative of that. You can use that in general every single time, because the derivative when it's just x would be 1. Questions on that? Okay. You thought that was all, but there's still one more way they can mess with it. Okay. We'll go decently basic. So let's say, what have we not used yet? H of x? Sure. H of x equals the integral from x to 3x squared. Ooh. The square root of t squared minus 1 dt. Find h prime of x. Okay. Here, we don't have a constant anywhere, right? we have our bounds are both based upon functions. I'm going to tell you how to do this, and then I'll show you why it's true. So essentially what we do is think of it again in terms of f of b minus f of a, right? We take the upper bound substituted in minus the lower bound substituted. That's essentially what's happening. So all we do is we're going to take this, substitute it in. So instead of t squared, I have 3x squared minus 1. Pause to make sure we're good here. So if this was a constant, we would just go ahead and substitute in. We have 3x squared minus 1 times the derivative of 3x squared, right? Because chain rule here. So times good 6x. So if that would have just been a constant there, that would be your answer, right? But it's not just a constant, which means when I take the derivative of it, it doesn't just go away. Because when I took the derivative of constants, it went away. But it's not a constant, so it doesn't go away, so it means I need to consider that as well. So so it's still going to do minus that next piece. Before, though, we knew that went away, so we didn't bother with it. Since it doesn't go away, we do have to bother with it. So now I just simply take x and put it in. Technically, multiply by the derivative of that bound. What's the derivative of x? Just 1. You can write it in, but you don't really need it. Oh my goodness, I made such a big error in the beginning. I said these were equal. They are not. H prime of x. That was close. I almost lost all my points there. So you take your first one, put it in like normal, do chain rule. Then you just do minus the bottom one, put in chain rule. It's like f of b minus f of a. You evaluate your integral with the upper bound minus the integral of I evaluate the lower bound. So that's all that changes. If you don't have a constant here, what that means is when you take the derivative, it doesn't go away. So we do have to go ahead and consider that as well. Now I will say be careful. Here, we didn't necessarily need parentheses because it was just one item there. But sometimes it is multiple pieces in which you need to have parentheses. Oh, they love or stuff like that actually. Where you would then have to distribute that. But this would be your answer. No complex fractions. No. What is it? No, it's fine with that. I just don't. I want to make sure you know my square root ends. Yes. This right here. So if this would have been a constant, then when we take the derivative, remember when we did it and got a bunch of numbers here, we took the derivative that ended up being just here, right? That went away. But this is not a constant, so it doesn't go away when I take my derivative. So I have to do this piece as well. So my first piece is just that plugged in times the chain rule of it. So my second piece is just that plugged in times the chain rule of it. Chain rule of x, though, is just 1. So it's this plugged in, chain rule, minus this plugged in. Okay? See me and you still control. Questions on that one? Okay. So if we go back to that problem that we were doing in the beginning, this is why when I take my derivative here, oh look, 0 to x, right? So if I do my FTC part 1, sounds so cool when you say it that way. My derivative of g of x is simply taking my x and putting it in, right? My derivative of g of x is just f of x. It's that FTC part 1. So then when it says find all the values of x on the open interval at which g has a relative maximum, we want to know when g prime of x changes from positive to negative, which what that means for us is really, when f of x, because that is g prime of x, changes from positive to negative. That's how we can use the chart or the table, the graph, to help us actually interact. Okay, so next class we'll come back to this beginning class and kind of take a look at it. All right, your homework for tonight is 3-4. It's soft.
Wait, one page?
I feel like I'm letting you. Now again, don't be freaked out once you start seeing a trig, because we don't know the derivatives trig, but sometimes you don't even need to take the derivative of a trig function.
You're not about to ask us about
Is there anyone that does not get this?